In the history of science, some ideas are so brilliant they change everything, even when they turn out to be not quite right. And that is the exact story of the Bohr model of the atom. Back in 1913, Niels Bohr came up with this picture of the atom that was absolutely revolutionary. I mean, it solved puzzles that had left the best physicists totally stumped. But, and this is the wild part, it was replaced in less than a decade. So today, we're going to unpack this flawed masterpiece, a theory that was a huge success and a huge failure all at the same time, and see why it was such a crucial step forward. All right, here's our game plan for this explainer. We'll start with a pre-quantum puzzle, then get into Bohr's revolutionary model itself. We'll see how it managed to explain atomic spectra, look at the cracks that started to appear in the theory, and finally, wrap up with the legacy of this incredible stepping stone. So first up, the pre-quantum puzzle. To really get why Bohr's model was such a big deal, you have to understand the mess that physics was in at the time. There was this picture of an unstable atom, and honestly, it was a total crisis. The existing theories just couldn't explain what scientists were actually seeing. And things were moving fast. I mean, just look at this timeline. In 1904, you have J.J. Thomson's plum pudding model. Basically, the idea that an atom was just this blob of positive goo with electrons dotted through it. Just 7 years later, in 1911, Ernest Rutherford completely flips that on its head with his nuclear model. Suddenly, we have a tiny, dense nucleus with electrons orbiting it, kind of like planets around the sun. And then, bam, 1913, Bohr's model arrives. But that planetary model from Rutherford, it had a massive, and I mean fatal, flaw. Okay, so here is the heart of the problem. On one hand, Rutherford's experiments were solid. They showed that atoms had this tiny nucleus with electrons orbiting it. But on the other hand, the laws of classical physics, the physics of Newton that had worked perfectly for centuries, screamed, no way. According to those laws, an orbiting electron is constantly accelerating, and any accelerating charge has to radiate energy. So what does that mean? It means the electron should lose energy, spiral inwards, and crash into the nucleus in, well, a fraction of a second. Basically, classical physics predicted that atoms couldn't possibly exist, which is a problem, right? Because here we are. And if that wasn't enough, there was a second, totally bizarre puzzle. When you take hydrogen gas and you zap it with energy, it glows. But it doesn't just glow with any old light. It emits light only at very specific, discrete colors, creating this kind of barcode pattern of light. A scientist named Rydberg had even come up with an equation that could predict the exact position of every single line in that pattern perfectly. But here's the kicker. Nobody had a clue why the formula worked. It was just this magic recipe that gave the right answer, with zero explanation behind it. So any new theory of the atom had two huge problems to solve. Why don't atoms collapse, and what's with this weird barcode of light? All right, section 2, Bohr's revolutionary model. This is where Niels Bohr steps in and decides, you know what? If the old rules don't work, let's just make new ones. He basically took Rutherford's planetary atom, sprinkled in some brand new ideas from quantum theory, and came up with something that was a complete game changer. His model was built on a few incredibly bold assumptions, or postulates. First, he just declared that electrons can be in special stationary orbits where they don't radiate energy. He basically said, that classical rule, let's just ignore it for these specific orbits. Second, he said that not just any orbit is allowed. An electron's angular momentum, you can think of that as its quantity of rotational motion, is quantized. That means it can only have specific discrete values, like rungs on a ladder. You can be on rung 1 or rung 2, but never in between. And third, he said electrons can jump between these allowed orbits. If it jumps down, it spits out a little packet of light, a photon, and if it jumps up, it has to absorb one. And the energy of that photon has to exactly match the energy difference between the two rungs. And the story goes that Bohr was talking with a colleague who mentioned the Balmer formula. That's part of the Rydberg formula for hydrogen spectrum. And for Bohr, it was this massive eureka moment. He later said, everything became clear. He instantly saw that his idea of quantized orbits and these electron jumps was the physical reality behind that mysterious math. And this model gave us a crucial new concept, the ground state. It's simply the lowest possible energy level, the bottom rung of the ladder that an electron can be on. And once it's there, it can't go any lower. It can't radiate any more energy. Boom. Just like that, the problem of the atom collapsing is solved. There's a built-in stopping point. So what happens if you pump energy into the atom? Maybe you heat it up or zap it with electricity? Well, that energy can kick an electron up to a higher energy level further from the nucleus. We call this an excited state. But that state is unstable. It doesn't last. The electron wants to fall back down to the ground state. And when it does, it spits out that photon of light we talked about. And this right here is what led to the model's greatest triumph. Section 3, explaining atomic spectra. This is where the Bohr model went from being a crazy idea to a Nobel Prize-worthy theory. Because it didn't just solve the stability problem, it perfectly explained that mysterious barcode of light from hydrogen. So let's circle back to this puzzle for a second. The Rydberg formula. It was this amazing equation that could predict the light from hydrogen without fail, but no one knew why. It was kind of like having a key that always opened a specific door, but you had no idea what the inside of the lock looked like or why that particular key shape worked. Well, Bohr's model was the solution. It provided the why. Using his new rules, he could calculate the exact energy for each of those allowed orbits, each rung on the ladder. And the energy of the photon released when an electron jumped from a higher rung to a lower one matched the Rydberg formula exactly. But here's the most incredible part. He didn't just match the formula. He was able to derive the Rydberg constant, the magic number in that equation, from other, more fundamental constants of the universe, things like the mass and charge of the electron and Planck's constant. This wasn't just matching data. This was explaining it from first principles. And the predictions were just spot on. For example, his model calculated that the energy of the ground state for a hydrogen atom is negative 13.6 electron volts. And when scientists went and measured it, that's exactly what they found. This wasn't just close, it was a perfect match. For the physics community, this was a stunning, stunning confirmation. The theory worked. Okay, so the model was a huge success for hydrogen, but science never stops pushing. And as physicists tried to apply the model to other, more complex atoms, some serious cracks started to show. It turned out to be an incomplete picture. And here's where it all started to fall apart. First, the model only really worked for atoms with a single electron, like hydrogen. The moment you tried to use it for helium, which has two, the math just failed. It couldn't predict the spectra at all. It also couldn't explain something called fine structure. When you look really closely at a single spectral line, you see it's actually made of several, even finer lines. The Bohr model had no answer for that. Or for the Zeeman effect, where those lines split apart in a magnetic field. And on a deeper level, it was just wrong about the nature of the electron. It treated it as a simple particle in a fixed orbit, completely ignoring its wave-like properties. And it flat-out violated one of the cornerstones of modern quantum mechanics, the Heisenberg uncertainty principle. So really, the biggest problem was that the model was built on what scientists call ad hoc assumptions. That's a fancy way of saying the rules were kind of just made up to fit the facts. They worked, sure, but they didn't come from any deeper theory. Bohr's model was this weird, clunky mix of old-school classical ideas and these brand-new, not yet understood quantum rules. And so, the end came pretty quickly. In the mid-1920s, a much more complete and powerful theory came along: quantum mechanics. People like Werner Heisenberg and Erwin Schrödinger developed a whole new framework that threw out Bohr's simple planetary orbits and replaced them with something much weirder and more accurate: the idea of electrons as waves of probability. So that brings us to our last section, the legacy of this stepping stone. You might be thinking, okay, so it was wrong and it got replaced. Why do we even care about it today? Well, because its importance goes way beyond just being a correct or incorrect theory. Even though the model itself is obsolete, some of its core ideas were absolutely revolutionary and are still fundamental to physics today. It was the Bohr model that first introduced the concept of quantized energy levels, the idea that energy comes in discrete packets. And it gave us the idea of quantum jumps. These two concepts were so powerful that they survived the death of the model and became foundational pillars of modern quantum mechanics. And then there's the cultural legacy. That visual, the little nucleus with electrons whipping around it like planets, it's just so simple and powerful. It became the symbol for the atom, for science, for nuclear energy. And even though we know it's not what an atom actually looks like, that image is still everywhere today. You'll see it in the logo for the International Atomic Energy Agency, the logo for the coding framework React.js. It's an icon that has truly lasted. And that really leaves us with something to think about, doesn't it? The Bohr model was a brilliant, revolutionary idea that pushed science forward in a huge way. And yet, it was just a stepping stone on the path to a deeper truth. It really makes you wonder what scientific certainties that we hold today might just be the flawed masterpieces of our own time, just waiting for the next great breakthrough to show us how much we still have to learn.